My name is Felix Wacht, and I want to present together with my colleagues Jonas Rosser, Andreas Rupp, and Yannick Klirovalek from the UMCG. It's the Universal Hospital in Groningen. Our work that we have done in the project AirMur that was funded by Horizon, where we discovered how the potential of a medical drone when transporting a person to the emergency side would look like when we go into a microscopic traffic analysis. So there are some literature that you can do. Most of them they are for transporting medical goods, but especially I want to show something that was quite useful for us. The study from the E&M, the ADC volocopter, they cooperated so that ADAC can use the volocopter in their rescue service, and they're going on with their topic. And after this study was presented, a lot of projects were founded. Under these projects, there were the project AirMur where we worked in, but several other projects. The topic of the AirMur was focused on the urban environment, and there was the statement, how can the transportation of goods but also person can gain the time benefits in urban cities, or actually it was more like a fact that in urban city that is quite good. But we wanted to prove it. It was not really proved before. And what to say that the person drones, at the moment, you cannot see them fly. Some of you have heard that maybe volocopter will fly this year. I think so, but we don't know. But all the other drones have not a certification for the Europe environment at the moment. And the performance of the different drones, they vary. You have to choose your system, actually. To go to the research question, the picture that you see is Stavanger city. The first research question I already mentioned, how does the behavior looks like when you use the microscopic traffic analysis against some simple drone model. But to understand the second question, we have to look to Stavanger city, like that's Stavanger city, and they have some islands at the near north area, and to reach the north areas, then you have taken some bridges. There's just one road that is connecting over this side, and on the other hand, you have some surrounding environments on different other city parts or cities actually. Like this could be some interesting, and the borders in the east, and that is really not the area where normally the hospital interacts, but here there is like the seawater, and it's not far away for a drone. So if the drone is positioned at the hospital, that is this point, that it could be really useful for Stavanger. So before we go into the microscopic traffic analysis, we know that there are some places that would really fit for the system. So the next question is, how can the clear advantages actually, this one and maybe these ones, can be identified, and we can make some generalistic results that can be transferable to different other cities. We have done the study for Stavanger, as we said, because they were project partners and we have a lot of data and discussions with them, and also for the EHang 210, that was the second drone that I showed before. They were also partners, and we could talk to them how they would show up their strategic planning for the missions. So our methodology was that we used Sumo, for sure, that's the reason why I'm here, in 3 different traffic scenarios, in rush hour, normal state, and nighttime, traffic time. We looked on, we imported the road network that we have to do. We calibrated the traffic. We looked on the car following model. I will go to it in the next slides, and the ambulance behavior in a different way that we've seen the presentation before. And we made more or less equally distributed destinations to get an overall view. And then we take synthetic drone data, we made like a small model. It is not time-based. We know where they want to fly, we know the distances where they fly to, and we calculated with cruising speed, ascending and descending speeds. And we looked on some variations through the wind speeds or different drone models. And then we transformed the results to traffic time benefits, and for the different beneficial states. The different beneficial states come together with a best case and worst case scenario for the ground traffic, and the best case and worst case for the drone flight. That depends on the wind speeds then. For the definition of the general behavior, we had two possibilities. I will not show the first one because of presentation time, but the second one was the better result, so you will see how we fitted this. It is the dependence between the travel time and the distance traveled by the ground relation. And we will make some quantitative statements out of this and make a future outlook through the speed variations of the drones. So looking on the traffic calibration, we had some traffic counting data. It is open source, so that was beautiful in the northern areas. So it's not common in all the cities, in the bigger ones there it is actually. And we had to make some match mapping to choose the sectors on our simulation network to fit into the counting data. Therefore, we used Leuven map matching algorithm in Python. And we scaled the mean traffics to have a representative model. You see the scale factor in the right figure. Over the time of the day, we have a variation of the mean traffic. Like 1 is the mean traffic, and then you can choose like a time that you want to fit in, and then you have a representative traffic behavior, more or less. And the variations, the standard deviation, came through the different road sections, because they will not scale similar, but we can see like a quite good trend there. And now coming to the car following model, we used EIDM, a model that is maybe too accurate for our purpose, but we had a lot of knowledge with it, and we calibrated it in some previous projects. So we know with our parameterization the cars behave like they should, and we have a quite good model, we hope so. Yeah. So coming to the ambulance interaction, I don't have to say too much because you already know what happens. What I want to say is that we can skip that, and we can actually skip that because we know it. But when we looked at the simulation and ambulances can cross the oncoming lane, then we had a lot of errors, and the system crashed regularly. Actually, you had yes, I already heard that maybe you have fixed the problem almost, or 2 days ago. Yeah. So maybe in the future that is not coming. So we have deactivated that, but we also checked if the ambulances can reach the rescue lane, and therefore we set down the lateral buffer zone between the civil cars and the ambulances from 60 centimeters to 5. Actually, that's not much, but in general, after all, our trend has to fit in the real data. And with this calibration, it worked quite well. We set the lateral alignment to almost left, but with this calibration or parameterization, the ambulance has the shortest way to the rescue line, and the willingness to encourage laterally on other drivers to 100%. I think the standard parameterization is at 0, a small number. Yeah. And to define, now we can came to the definition of the destination points. We looked on the whole map. So we take a grid over the whole map, and then we choose our destination points with a next node algorithm, so that we can assign our destinations to our trip data with a from and a to junction key. The from junction, for sure, it's the hospital, and the to junction are all these points that we fitted near to the grid points. And then another thing that we've made is that we launched all ambulances in the same simulation, but we had a buffer time of, I think it was 60 seconds, and they are chosen in random order. So if we make one by one, and we had a grid, so they will all drive to the same direction, and maybe they could interact, and they will change the traffic time, so we make it randomly with a buffer time, so they don't interact with each other. With these configurations, we had some statistic data from Stavanger. We could fit quite well in the linearization between the mission distance, the travel time on the ground, travel distance on the ground, and the travel time. When you think about we are simulating EMS services, 70 minutes, it's quite a lot. We already had the log data from the past 10 years of them, and we looked at them, and they behave quite similar. I wanted to plot it as well, but there is a change because they cut off the maximum driving time at 60 minutes. So as long as we have more mission or can get closer to 60 minutes is about here to this point, our mean travel time will, like here it fits quite well, and then it goes down, but it's because of that cutoff. So it was not perfect for showing here, but we've seen that we have missions that were really like 60 kilometers, 70 kilometers, and that is more than the area that we have observed. We have talked before to the city, and they said they have the small area. We already extended it, but there were some trips, maybe if another hospital cannot serve their services, that they really drive through a few cities and they serve there. That's the only slide that I have to the drone calculation model. As I said, we just calculated the distances and the speeds, and we have a static model. But we looked inside of the energy consumption and more the behavior to prove why we have chosen the simplified model and why we have variated the travel speed through the wind speeds. The reason was that when you have a fixed airspeed, so at the x-axis we have the relative speed to the airspeed. If you have a fixed airspeed, you have a fixed power consumption. And as long as you try to be on that stable point for your global calculation, for your mean traffic speed, you have power reserves for wind peaks. And as long as the wind gains, the peaks will gain, and you need that safety criteria. And to look on the Stavanger wind map, they worked on the statistic plot. I really like this one. You can see the average number of the wind speeds. It is the average of the average is about 20 kilometers per hour. So that is the definition that we have made. You have more peaks, but we wanted to cover them as a peak. And the worst and the best condition is when the mean wind speed comes headways or tailways. That's our definition. So I directly come to the first results. So these are the numbers, and the colors we gained some of the numbers, maximum 3 by 3 of the destination points, to give a visual plot for the time advantages between drones and ambulance times. The first one is the normal case. The second one is the best condition for the drone. So we had the tailwind. The drone is a bit faster than defined, and we have rush hour on the ground. And the third one is the opposite way around, the worst case for the drone. We already mentioned that the drone will not reach the outer spaces because of when they're flying slower, so they need the same energy in the same time, and they could not make the same distances then. But we see what I said at the beginning. that in the area that is not served normally, you have huge time benefits for sure, because the ambulance has to travel. It has to travel to the south, almost to the south, and then coming up again to reach this point. There are emergency boats, but they are not located here. They are located here. So if the boat has to come to the hospital and then go to the other side, you have actually the same time. I don't know why they're choosing this. So that's the obvious time benefit, what we want to go further. Therefore, we take the relation between the time benefit that you calculated, time benefit on the x-axis, and the distance traveled on ground on the y-axis, and the distance traveled on ground on the x-axis. And we already can see that there is a linearization. It's the black line, and we have a cluster of missions that have something like a peak here. I want to go ahead to the next slides with the information. These points are on these eastern islands. So that plot, or that fits quite well for our mission, what we wanted to do. And we try to make a buffer around the mean behavior so that it does not cover the points on the other island. Therefore, we had a buffer of 10 minutes between the mean travel time behavior and the cutoff for our normal behavior state. So between the two red lines, that are the missions that we define as a generalistic behavior that could occur in different other cities when they have not a complex street network. Let's take it by that. So the upper one were over the envelope, the lower one under the envelope, they're not too much. And then we divided it further to the upper envelope and the lower envelope. So inside of the envelope, but the better half and the worse half. If you read the AGB, it's the average generalistic behavior. I just wanted to shorten the term. So that's the map on the same thing that we have seen before. And the first clustering, these clusterings are the method 1, where we wanted to fit the travel time benefits against the distance to the next primary road, defined on OSM. Primary or higher, highway and primary, yeah. That fits okay, but was not the best solution, so I directly choose to present you this part. The dark green ones are the 10 minutes better than the HEB, so the outer upper envelope, so better than the envelope. The light green ones are the better half inside of the envelope, the black ones the worst half or inside of the envelope, and then we have some orange ones. I don't want to cover this. But that is interesting because at the beginning we said that we want to prove that in urban environment there is a potential on the drones, even if the hospital isn't far away. Here it's the city center and there is the hospital. But you can see that when you look on the generalistic behavior, the missions that are a bit better than the mean travel behavior, they are inside of the main city areas where the population is quite high. So I know the map, so that this is a statement that comes from my side. But we also took the points and analyzed the population density, and then you come to the second graph, where you see when the population density gains, you have a bigger portion of the light green points. So it starts in a lower position, and then we have a rising mode. So we can say that in urban environments there is a beneficial scenario for the drones if they can land. Then we transformed all this data. So we combined the travel time gains with the population density, because the population density is a good marker for how often an EMS will be called in the area. Deployed, but there are some others, but the population density is the most drastic key actually. And we choosing this plot, so it's some histogram from the occurrence, how often these points will reach, and how how big the time benefits will be. And yeah, so this plot will serve all your questions actually, but I want to make some quantitative statements to guide you through that. So if we take the 80th percentile of the missions, we have for the normal behavior, it's for the normal generalistic behavior, but also for the average behavior in Stavanger, we don't have too much changes. We can say that we have about 10 minutes of time benefit, and that's the 10 minutes that I just mentioned here. And for the 80th percentile, we have for the most beneficial state for the ambulances and the drones, we had 6 minutes and 14 minutes as well. For the majority of the remaining deployments, in the most generalistic behavior, we had time savings about 10 to 20 minutes. So here we are almost on the 100%. That is quite much for the EMS services, and especially for Stavanger, where we have this 5%, it's about here, where we have bigger time advantages up to 1 hour. So that was almost our conclusion, but then we compared some other drone speeds. We put the generalistic behavior, the average behavior on Stavanger, and just variated the flight time to get an outlook. If we don't use the EHang 210, we will use some future models or some other models that can serve these speeds, 120 kilometers per hour or 260 kilometers per hour, how it would look like in this plot. And therefore, I tried to get some numbers out of this plot to make some simple statements. Don't take them too static. It's just that if you want to think about it, you can do it in 1 second if you take these numbers. So the 120 kilometers per hour are 50% more than the 80 kilometers per hour that we had, and the 260 are almost a double one. And if you look at the time savings for the 50th percentile, the 80s, 90s, and 95s, for the bigger portion, so for the fat numbers, you can see that the time savings are scaling similar to the speed savings. So there will be on the higher numbers, there will be degrees, but you can choose it for a bigger portion to just think about. And the other one, I don't have to plotted this, but these are interesting as well. If you look at the linearization between the travel time from the drone and the travel time related to the ground, you had a gain for about 1 kilometer, 0.1 minutes per kilometer driven, or in the other way around, we have 1 minute of time savings for each 10 kilometer of driving. We had some additional scalar offset as well, but that's are the numbers what I want to give you. So everything I said is in the conclusion now, just to read it while we have some discussions. And I mentioned some references, so there are the references in the presentation, but almost if you want to see something, these have the same numbers as in the paper, so you can directly go there if you want to check something. So thank you for your listening, and I hope that there are some questions.